Okay, welcome to the sixth and final live demonstration of the SunCell from the nation's capital. And we're here in the Homer building on the 12th floor to talk about and reveal to the world a new energy source that's superior to any other ever discovered. Involves reacting the electron of the hydrogen atom with a catalyst to form a more stable chemical state of the hydrogen atom, releasing enormous amounts of power, and it's completely green without any pollution, with tremendously less complexity in infrastructure and capital costs. So I'm going to introduce you to some of the equipment that we use, and then I'll talk more about the technology and the process and the business implications. So we have a, this is the main reactor cell body of the SunCell, and there's other ancillary equipment that goes on this. And in the cell, we form tremendously high power density on the order of 5 to 10 million watts per liter is capable. And then there's an external electromagnetic pump that goes on this line, and there's molten gallium, which is molten metal, that's continuously circulated through the system. So the molten gallium flows through a reservoir in the SunCell, and it acquires heat and then continues its flow through this shell and tube heat exchanger. And what that comprises is a bundle of tubes that receive coolant and transfer that thermal power to the coolant. So there's a molten flow, continuously recirculating, continuously transferring thermal power to a coolant that's dynamically flowed through this heat exchanger. So the coolant is either water. In that case, the exit, the output is heated water for hot water applications, and steam. And this particular device would produce between 1 and 15 atmospheric pressure of steam for heating applications, both residential and commercial, and also for industrial processes on the higher end pressure end of the scale. Alternatively, you can flow air through this with a blower, force air through, and produce variable temperature air between 100 degrees centigrade and 1,000 degrees centigrade. And at the higher end of that temperature scale, it can be mated with a microturbine to make electricity. So between the steam and the heated air, it can service the entire world thermal market. It's about 8 trillion a year, about half the world's energy load, and about 1/3 of the CO2 emission in terms of what it could eliminate. Ultimately, in addition to to supplant rotating machinery, we have a new innovation that's an advancement on magnetohydrodynamic technology. I'll get more into its history, but let me review what this is, this device and components. So it has a SunCell, a little bit different geometry. It's configured to make, again, extremely high power density, to build up pressure, and then to cause an expansion of a plasma that's maintained internal to the reaction chamber through a jet to create a supersonic jet of very highly conductive kinetic energy flow that goes through a magnetized chamber with transverse or perpendicularly oriented electrodes to directly convert that kinetic energy of that jet into electricity. That can occur with almost 100% efficiency, and the conversion of pressure and to particular thermal and energy that's responsible for the pressure, drives the pressure, can be converted into kinetic energy with almost 100% efficiency as well. So the combination, jet creation and jet conversion into electricity, can be extraordinarily high efficiency. And because of the characteristics of this plasma being extremely thermally conductive, it can have tremendous power densities, at least 100 times that of rotating machinery. When the plasma relinquishes its power to the electrical circuit, it's collected at the end of the channel and pumped back as a liquid by electromagnetic pump and recirculated through the reaction system. Okay, so then there's a product form, a Hydrino product. And this is one example of the Hydrino product. This is gallium oxyhydroxide. It's gallium ions with oxide ions and hydroxide ions that have a crystalline lattice that has trapped the Hydrino molecules in here. In particular, the Hydrino molecules are hydrogen molecules, but the electrons are more tightly bound in a more stable chemical form in a lower orbit relative to uncatalyzed hydrogen. This particular composition matter has been analyzed by electron paramagnetic resonance spectroscopy independently at a major world leading university, and the results unequivocally confirm that this comprises Hydrino and that Hydrino exists. About 50 spectral lines that are created by the absorption of specific frequencies of radio waves with the material in a magnetic field, very strong magnetic field. And the Hydrino uniquely comprises an unpaired and a paired electron in a single molecular orbital. And the interaction between those two and the transition of the orientation of that unpaired electron parallel and anti-parallel to magnetic field, it's a quantized transition, produces a series of spectral lines that match identically those predicted for Hydrino, and there's nothing known to man that has those types of signatures in those energy region and that energy pattern. So it's one of the many ways. We have over 20 methods of proving unequivocally the existence of Hydrino and the Hydrino reaction. So I'm going to go now into the technology and more the business and what the implications of this are. So we have developed a zero pollution primary energy source. That means it's not a storage or a converter, like storage like a battery or a converter like a solar cell. It's a new source of power. It's applicable essentially all power applications, and we're running it in internal thermal field trials at a scale of 100,000 to 250,000 watts, continuously producing steam at enormous power densities, 5 megawatts per liter or higher. And we also have multiple external programs that are in progress. It was theoretically predicted from classical physical laws that absolutely confirm that physical laws also apply at the level of the atom. That was actually what was intuitively known at the time of the creation of quantum mechanics, that of course physical laws have to govern the physical world, and they would ultimately be found to apply to the atom and the electron and subatomic particles. It just wasn't known how to solve those laws for those particular problems until now. And it's very, very big news that you can solve everything from subatomic particle masses to predicting the acceleration and expansion of cosmos and other cosmological parameters, molecules and balance, extent, complexity, and analytical exact equations that match identically data over 85 orders of magnitude of scale. It was absolutely essential to solve these equations to predict this power source in terms of the catalysts and the conditions and the signatures of the Hydrino reaction products and its unique properties. We built upon thousands and thousands of experiments, spent $120 million, spent decades developing this technology, which, for example, entailed specifically testing 6,000 different chemical solid fuel reaction mixtures, thousands of plasma cells, thousands of other electrochemical and other systems, and each one many different types of plasma cells and chemistries, and doing full characterization, all reactants and products and spectroscopy, more and more theory and more predictions, and advancement after advancement in engineering and prototyping and building first of a kind over and over again, new systems to advance this technology. The point now where it's commercially competitive and much greater than fire. We have it validated at over 300,000 watts without cooling. The reaction makes more power as it becomes hotter. So those systems were run without cooling to let them ramp up to the highest temperature possible before you melted down the reactor. To run it continuously, it requires cooling. And when we added cooling, we found that the reaction didn't work because the temperature was too low to sustain the reaction. So I invented a new ignition system that I'll explain a little later that makes the reactants behave as if they're 10,000 degrees or higher, even though they're very low power input and are running essentially at laboratory conditions. So this 100,000 watts now runs continuously. We've done 100-hour trials. It produces steam and can be used for thermal applications. The SunCell comprises the main components being a hydrogen and catalyst injection system to create the Hydrino reaction mixture, electromagnetic pump that injects molten gallium, which is a molten metal even almost at room temperature. It's the same metal that's in thermometers, and it serves as an electrode as well, and injects the molten metal to a counter electrode that completes a circuit and allows a very high current, low voltage current flow that triggers or ignites the Hydrino reaction and creates the power from allowing hydrogen or causing hydrogen to react to go to these lower chemical energy states, releasing 200 times the energy of burning the hydrogen. The hydrogen can become released from water by a simple process called electrolysis. It would consume a very less than 1%, a fraction of the output electrical power from the system. As I said, we have Hydrino in a bottle, and we've characterized it by over 20 spectroscopic methods and have a number of independent expert validations unequivocally proving Hydrino, in particular one that's been submitted that's independently verified the existence of Hydrino and submitted to a major world top tier journal. We have patents issued worldwide, and I'll go through the specifics. So man has been using fire for 1.5 million years, more or less. Fire is still being used today after all these years, and it obviously has limitations. It's right now producing CO2 that's polluting the atmosphere, the same as industrial air. It's very convenient to throw toxic waste in the river, but you can't do that forever. It has consequences. And the same with CO2. It is prudent to eventually eliminate dumping it into our biosphere. So we have something that takes hydrogen from water, creates a new, more chemical stable state of hydrogen, lighter than air, can't be contained in the atmosphere, but has tremendous commercial applications upon isolation. And that process creates the new fire, which is tremendously more powerful and versatile than burning carbon or hydrocarbons and hydrogen alike to produce water and carbon dioxide. So this is what it looks like inside the cell with high-speed video. The characteristic purple emission is from hydrogen emission. That's its characteristic signature of light. This is what it looks like from the external view. This is about 200,000 watts of steam production. So we're going to show you more than 100,000 watts today on demand. This is our 6th demonstration. All of them are run flawlessly. So our immediate goals to bring this to market are to pursue commercial thermal power sources in the 100,000 to 250,000 scale using support from external engineering firms, strategic partnerships with original equipment manufacturers, and outsourcing manufacturing. We intend to lease capital equipment on a per diem basis, on a time basis, and also use existing infrastructure, companies that do service work for the utility industry on multi-billion scale, and EPC firms, engineering, procurement, and construction firms that have lost work due to the downturn in oil and gas industry. There's a lot of infrastructure for the implementation of installation, beyond manufacturing, installation, maintenance, and depot repair of SunCells. So we are pursuing as well the outsourcing of the commercial packaging using a manufacturer and an engineering firm that has the capacity to manufacture an initial 100,000 unit per year scale, to be transitioned into a high volume manufacturer at millions of units per year. So we're going to support, and we're targeting strategic partners and customers for two different goals. One being to do original equipment manufacturer strategic partner deals to initially engage to produce a boiler type heat exchanger and also an air heat exchanger, as I described earlier. The air heat exchanger can be interfaced with a microturbine, so that's another target strategic partner, a microturbine original equipment manufacturer, OEM. The other side of the business being the consumption side, the customer side, we're supporting deals that we sell discounted green power as a pre-sale to become profitable. So we've developed a 250 kilowatt molten gallium to steam heat exchanger to produce hot water and steam that we're testing internally for the corresponding thermal markets. We've also developed a 250,000 watt molten gallium to air heat exchanger with the capability of variable air temperature of 100 degrees C to 1,000 degrees C to service the balance of the $8 trillion a year T with a T thermal market, which corresponds to 1/3, or the market corresponds to 1/2 of the world's power market, but it eliminates 1/3 of the world's CO2 emissions. So that's big. Even buildings is 1/4 of the world power market, that is doing heating for buildings. Very large, very easy markets within reach, very near-term reach of where we are today with the technology as it exists. In fact, this is a historic event. We are contributing to the heating of the Homer building here in Washington, D.C., which is equivalent to the Kitty Hawk. It's the first external industrial application of thermal SunCell Hydrino power source ever in history. So we're gonna make you part of that here in a second, so you can witness that. So achieving profitability and potentially even in tandem, we're looking to do magnetohydrodynamic with the incredible power density of 23 megawatts per liter and near unity efficiency with 1/10 the cost of conventional power conversion equipment. We're also sending the Hydrino out to independent laboratories doing things, analytical tests like electron paramagnetic resonance and Raman and other types of spectroscopies to independently validate the existence of Hydrino. So we have it in a bottle. It can't be argued that it doesn't exist because we have it on demand, and we can prove it by over 20 spectroscopic methods. So in the thermal market, as I said, we're going to look at the air and water heat exchanger, and then from the $8 trillion a year heating market to the 3.5 trillion electricity market using the Brayton cycle turbine. And then the magnetohydrodynamic is the ultimate device for electrical generation that enables all types of mode of applications beyond stationary power, being marine, rail, aerospace, trucks, cars, etc. Given that the hydrino is a very unique composition of matter, unlike any known, you can imagine there are extraordinary chemical applications, particularly high power, very short wavelength, molecular lasers, magnetic materials, and electronic circuit elements, logic elements, and magnetic storage that can surpass anything by many, many orders of magnitude. It has the same properties as a superconducting quantum interference device that can enable optical laser or optical computing with phenomenal minimal scale. It also produces, the reaction itself produces a shock wave with tremendous power and efficiency. That is, it's using very, very small amount of material. It's 10 times more powerful than TNT on a weight basis. And it's only coupling at the current stage 1% of the energy into that shock wave. So that can be used for construction and mining and propellants and other types of applications. So I'm going to transition now to the demonstration of the SunCell at over 100,000 watts. It's our sixth and final demonstration, and we hope you enjoy it. We'll come back and talk more about the chemistry and the commercial applications of the power.
Good afternoon, ladies and gentlemen, and welcome to an off-site demonstration here in Washington, D.C. Of our SunCell in action. And what you can see here in front of your screens is actually the SunCell running underwater in real time, just to show the tremendous output capability that we have in terms of the thermal energy that we can get out. I just wanted to give you a very quick overview of the SunCell and kind of how it works. To start, we have a gallium reservoir inside the cell, and that is constantly being mixed using an electromagnetic pump. The pump actually has a secondary purpose. We actually use the pump to inject gallium against a tungsten electrode, and at the point of contact between the tungsten electrode and the gallium, which serves as a counter electrode, we can supply a little bit of input energy, electrical energy, and fuel to kickstart and maintain the hydrogen reaction. Now, the electrical energy comes in the form of a DC power supply, and our fuel actually consists mostly of hydrogen. We use gaseous hydrogen here in the lab or for demonstrations, but actually we take the gaseous hydrogen and condition it with a low voltage plasma to convert it from diatomic molecular hydrogen to monatomic hydrogen. This hydrogen is then reacted with trace oxygen to produce freestanding water molecules, which are then injected into the SunCell, which allows the hydrogen reaction to kickstart and generate tremendous amount of thermal energy through a low voltage, high current plasma. And one thing I wanted to kind of show you is this plasma has a tremendous thermal output, and you can see the really strong boiling that we can see in the water tank. It's almost vigorous to the point where it's splashing out of the tank. This just showcases the amount of thermal energy that we can get out. And it's even more evident so if you look from the side, you can see on the surface of the tank, the side of the SunCell is actually producing very large bubbles of steam, and that just points to the fact that we have nucleate boiling and a large amount of heat transfer heat is being transferred from the SunCell to the water around it. This is actually also the reason why we use liquid gallium, because it's such a great thermal conductor that it can absorb the heat from the plasma and heat the SunCell evenly. We've done the theoretical calculations where we've seen that the amount of energy you can get out from combustion of hydrogen and oxygen is only on the order of a few watts per mole. But if you have the SunCell and you can conduct a Hydrino reaction inside, the capability goes up to almost to the scale of few hundreds of thousands of watts. So just wanted to kind of give you a live demonstration, and if you have any questions, please feel free to direct them to our chat or to the Q&A session that will take place after the presentation, and we'll be happy to answer them for you. Thank you.
Okay, well, it's good to have you back, and we hope you enjoyed that demonstration and history in the making. So on with the presentation. So as I said, we've done electron paramagnetic resonance with these unique signatures, and that particular signatures, each one of those characteristics of the radio frequency absorption identifies that you can use this as a equivalent to a logic circuit or a memory element in the electronics of tremendously small scale, orders and orders of magnitude smaller than transistors, because it has this squid or superconducting quantum interference signature. Remarkably, and probably for the first time ever, it turns out the Raman spectroscopy, which measures the rotation of the molecule, also records the same signature, but at a 1,000,000 times higher energy scale. So these are using lasers. So this shows you can use this, this molecule as that particular electronic circuit element using optical computing systems, or enable that. Remarkably, these energies are very, very high for rotation. Typically, it's about just to give you an energy scale, 121 reciprocal centimeters for rotation, and it'd be like 4,400 reciprocal centimeters for vibration. Even the rotational energy levels are at extraordinarily high energy, 15,000, for example, for rotation, like huge energies, and it's enabling of molecular lasers of very, very short wavelengths and very, very high power, for example. But also it has other astrophysical implications, because those rotational frequencies match the spectral bands called diffuse interstellar bands, which are seen all over the universe of unknown nature after many, many decades, well, actually probably 5 decades of study and attempt to elucidate what these are. There's other signatures, astrophysics phenomena and mysteries that this resolves. For example, there's continuum extreme ultraviolet light from all over the universe of massive power, 5 times more than all the emitters in the universe combined, and that matches the spectrum from our cell that we've achieved at 20 million watt peak power from a 10 microliter shot. Enormous power densities. We also see signatures from electron beam emission that we actually have to go from take the 0.515 electron volts of ordinary vibration, or the vibration of ordinary molecular hydrogen. It's 16 times that, which is over 8.25 EVs, which puts it in the range of ultraviolet emission for vibration. Unprecedented, same rotation, extremely high, 0.0159 EVs as an energy unit versus reciprocal centimeters. That puts it at puts where Hydrino is at 16 times, being 1940, for example, and then there's other transitions beyond it that put it out in the very, very high energy range, up to 15,000, 20,000 reciprocal centimeters, way beyond anything that any known composition of matter is capable of producing in terms of energy absorption or emission. We see that in the infrared, in the Raman spectroscopy, we're producing a new gas that has a faster migration time and higher thermal conductivity than anything known. So it's the prior being nitrogen and helium. So it's a unique characteristic from the gas that we collect from that cell you observed by cryogenically collecting it. That is collecting it at extremely cold temperatures. So we have X-ray photoelectron spectroscopy. That's another method. We measure the total energy of all the 2 electrons in the molecular orbital. It's absolutely dispositive. There's nothing else that has anything remotely in that region or that energy as a single molecular orbital. We have chemical compounds we see by high resolution mass spectroscopy that has hydrogen bound in it in unique ways. We can measure the magnetic properties by methods, nuclear magnetic resonance, magnetometry. We look at high performance liquid chromatography, show new characteristics of inorganic compounds when we bind this material into it. We have energetic signatures, a number of those in terms of population inversion, extraordinarily high temperatures of the hydrogen selectively. We have We have energetic power balances from solid fuels, from electrochemical cells, and from the SunCell, many different signatures of the Hydrino reaction that are way beyond that of a conventional chemistry or priorly known. To go into more of the mechanism, I explained that somewhat prior, but this gives me a schematic to explain the chemical processing. So there's a positive electrode at the top of a glow discharge where you apply a voltage relative to the cell body and flow gases at about 1% atmospheric pressure through this fuel processor. It creates atomic hydrogen and trace amounts of HOH catalyst. The molecular orbitals of HOH match those by a factor of 3 relative to ordinary hydrogen. So there's an integer match between atomic hydrogen, atomic orbital, and HOH molecular orbital. So there's an energy transfer that's radiationless through space interaction that allows the energy to be transferred from atomic hydrogen catalyst. It gets ionized in the process. We need to have the HOH to maintain this reaction. So that's created in this reactant processing apparatus system on top of the cell. There's a reaction mixture that's processed, goes into the reaction chamber, and we have the molten gallium pumped by this electromagnetic pump. It has a permanent magnet in this particular design. There's actually 2 stages of this to increase the mixing. So the gallium temperature is on the surface is maintained below 2300 centigrade, so it doesn't boil. So that's keeps the pressure in the range, which we get a very, very strong reaction. So injects that molten gallium against the counter electrode. We run a high current, low voltage through that completed circuit, and that recombines the electrons and ions and sustains high kinetics of the Hydrino reaction. So we found that we put this in water, the wall temperature on the outside and the reaction temperature on the inside are very, very similar. And that's too low to sustain the Hydrino reaction. It's akin to trying to burn underneath having a submerged combustion chamber underwater where it's very cold. So it's chemically driven. Chemical reactions have high kinetics at high temperature, and that's it. So this plasma ignition source on the top of the cell, this chemical processor using this glow discharge, creates the equivalent of those reactants being at 10,000 degrees centigrade or higher, even though there's very low power, and this is actually submerged in the water, and the temperature of this system is very, very low. That was very critical to allowing for the permitting continuous cooling of the SunCell while maintaining very high power levels that you observed in the current demonstration. So the SunCell develops the power, and then there's this flow of the molten gallium that's propelled by electromagnetic pump, and it propels it and pushes it through the heat exchanger, which is a series of tubes inside a shell where the coolant, being either water or air, is pumped through and collects the heat in an exchange with the hot molten metal flowing in this circulating loop. So in addition, that hot air can go into a gas turbine, as mentioned previously. This is an example of a validation that Dr. C ran. He's a noted professor at Rutgers University. Here's some of the numbers. It had, in this particular run, 91,000 watts of input power to run the ignition system by flowing high current on the order of 1,500 amps to up to 3,000 amps. I think this was more like on the 3,000 amp because it's very, very current dependent and temperature dependent. The higher the current, the higher the power. The reaction that developed 20 million watts at 250 times gain. That was 35,000 amps at about 6 volts. So this is on the order of maybe 1,000 to 3,000 amps if we were run these types of trials. So that had 91,000 in and 433 out for a net of 342,000 watts produced by the Hydrino reaction, which is between 4 and 5 times more power out than put into the ignition circuit. But keep in mind that the power at the end was much greater than 433,000 watts because the power in the beginning was essentially zero. It scales up as the temperature gets higher and higher. So this was very, very high power. Well over a megawatt, half a megawatt. So excuse me, half a megawatt. So if you have that kind of power, you can only run this. It's got the cell comprising a very large molten gallium reservoir to absorb that heat and a heavy stainless steel body to absorb the heat. We ran it up to the point where the system was just short of melting down. And then we dropped that into 500 pounds of water, releasing steam so that the weight of the water decreased, and also it warmed up the tank. So we could weigh both of those parameters with a very sensitive scale that was on a lever that had a counterbalance water tank. So we'd have very high sensitivity and water weight loss. In addition, a very high accuracy of the temperature increase in this water tank due to that stored energy in that cell when we dropped it in. So we could achieve better than 1% accuracy. And this cell was measured on an average basis to make 342,000 watts. And that was in a very small reaction volume of about half a liter, very high power density. So as I mentioned, we have to have the glow discharge fuel processing system on the top of the cell in order to get the equivalent of very high temperature reactants, that is to make the monatomic hydrogen and the HOH catalyst to flow into the cell to achieve those reactant conditions without having the cell wall capable of achieving very high temperatures. That is, in a water tank, the external wall is really decreased in temperature because of the steam production and the high heat transfer rates at that surface. So we showed in a validation run by Dr. Mark Nancy, who will talk later, that there's a very strong temperature dependence and also the requirement of this ignition system to sustain high continuous power. These cells were run, let me give you an example. This molten cell is run for a couple seconds. If we ran it for another half second, it would have melted down. But that was almost 1 million joules in that very, very short period of time. That is a huge amount of output power. So, and energy. Like that was enough to basically melt the whole system down, warm it all up, the gallium reservoir, and melt it down. So the goal was to run it continuously. So these cells were running for much longer duration. So they were typically run for 2 minutes, 3 minutes, etc. And they could sustain that longer period on the order of 10 times longer, 100 times longer, depending on how much steam we could tolerate being boiled off. But at least in this case, 100 times longer. And we lost about 25 pounds of water in under 2 minutes. And that corresponds to an output of a net of 100,000 watts of extra power. Subsequently, and particularly in the cell that you observed today, we've added carbon liner, we added refractory metal liner, and that cell can run at much higher temperature. This internal temperature was around 425. The one we ran just now was more like 750, and the power more or less doubles over that temperature increase. So these are the parts of that cell. This is showing the glow discharge system, the process, the reactants. This is a 2-stage electromagnetic pump showing transverse permanent magnets. And then there's little electrodes here where current runs through. This device consumes very low power. The voltage across here to drive high current, the electromagnetic pump section is only on, it's less than a volt. And this is known technology. It's been around for more than 60 years. In fact, I talked to some of the manufacturers. They say they still have 60-year-old devices, maintenance free in the field. So this is like forever technology. And it pumps the molten gallium through this nozzle and shoots it against the counter electrode and completes the circuit. This is a reaction chamber where the plasma is maintained. And then, as I said, we have these refractory materials around it. We use a particular kind of steel. It's very permeable, the Hydrino. That's another aspect. If it doesn't allow the permeation of the Hydrino product out of the reaction chamber, then it won't work. So a lot of technology in this. It actually is a lot of innovation went into the SunCell. So this is the different parts, and this adds up to about $3,800 for 250 kilowatt, or about $15 a kilowatt, and has no moving parts, and it all the parts are recyclable. So this is what the heat exchanger looks like. It's kind of in the background here. There's a series of bundles of tubes, and the molten gallium flows through those tubes and goes into a manifold and then undergoes a continuous recirculation loop. So the SunCell pumps in the hot gallium, and then it flows through this heat exchanger, and then there's coolant going in the opposite direction, either water or air, and out comes the hot coolant. You can also have a plurality of heat exchangers that do 250 kilowatts. It'd have about twice the diameter, about the same length as the one I showed you in the beginning of the presentation. So this adds up to about $8,000 for 250 kilowatt unit, which is about $20 a kilowatt. And you add that to 15, you have about $35 a kilowatt in a thermal system. So that is very, very competitive in terms of capital costs. So you're buying some electricity, and we've gotten the gain up to 10 times. So buying a little electricity doesn't really affect the economics. But if you wanted to look at it in terms of a standalone system with no grid connection, you could add a Brayton cycle off-the-shelf technology turbine. And as long as the gain of the SunCell is at least 3x, it will produce standalone thermal power of the total power output of the SunCell. So whatever gets converted into electricity will go back into the SunCell and be thermal. So it's all part of the thermal output. So you can have a standalone system without grid or fuels infrastructure as a thermal unit to service the $8 trillion a year market without buying electricity. And anything above 3x, you can sell net electricity. And if you go to magnetohydrodynamic, as next generation is almost 100%. And that is incredibly competitive in thermal and in electrical power production. The gain numbers we've seen, 5x is really, really easily achieved. We've gotten to the point where the silver cell, we know from experimental results that it can run on its own with no ignition power, and it appears it'll do that pretty much indefinitely. So the gallium cell, we're pushing to higher and higher temperature, and we have seen that the gallium cell for some period of time, for a minute or several minutes, can run on its own with no ignition power. And we feel we'll see the same phenomena with that as well as we push to higher operating temperatures. The gallium can form alloys with metal, which the silver does not, with stainless and the metals that we use. But now we've added carbon liner and refractory metal liner, particularly tungsten, which we've never seen an alloy form. So that's allowing us to go to higher and higher temperature, and we're continuing to test out that higher gain and higher power. So the turbine that I showed you, where in this schematic, takes the air from the compressor section, flows through these heat exchangers, and then goes out through the turbine section and turns a rotating shaft that powers the compressor, which drives the airflow. It serves as the blower replacement in the typical thermal application. And the shaft is common with the generator, so it can generate electricity. So it's commercially available technology. It's called external combustor, and Saldo, Capstone, and others make this devices. So we do not have to develop that. And we have done engineering calculations with other industry engineers, and they confirmed that the SunCell can be readily mated to one of these existing commercial devices. The capital cost is about $1,000 a kilowatt for large scale. And then over a period of 20-year lifetime, it has some maintenance and some other aspects that have to be upgraded. But overall, the impact is really, really nominal because the SunCell of 250 kilowatt scale can make around $250,000 a year. So it really is a tremendous revenue generating opportunity. And I was saying with MHD, it's phenomenally cheaper, at least 10 times or 1/10, 10 times cheaper or 1/10 the cost. Is another way to put it. So the MHD, as I was saying, it's a liquid metal nanoparticle cycle where the oxygen is desorbed out of the silver, and it creates high pressure and also nanoparticles. It creates pressure in the chamber. It gets expanded through the nozzle. The space shuttle nozzle, as example, is 99% efficient. Once you have a kinetic stream that's highly conductive, then it can be converted to electricity, extraordinary efficiency. It's like the reverse of a rail gun. And that's just two rails with a conductive projectile. You put a current through it with a magnetic field perpendicular and shoots it down the rails. This is kind of going the opposite. The projectile is coming down the rails in a magnetic field, and it outputs electricity. So the nanoparticles coalesce at the end of the channel, and they can be recycled and recirculated using electromagnetic pump with very little energy. If you try to make a complete cycle with a steam turbine, it's impossible. You have to use an external resource, namely water from a river or some other body of water that's cold. You can't condense the steam and chill it and then have it go back and complete the cycle. Air turbines, you can always find air as a heat sink, so that's more favored. But in the case of the MHD, the thermodynamics is extraordinarily favorable for complete cycle, closed cycle, where the nanoparticles coalesce and you're pumping back liquid metal with about 100 watts out of a couple 100,000 watts. If you had to even recirculate some form of seeding and some type of gas coming out of this gas expansion, like in case of combustion MHD conversion, you're looking at intercooled compressors, and it's just horrific in terms of how low efficiency that type of device is. So this is a phenomenal breakthrough relative to what was pursued in the past. And actually, it was widely acclaimed that it would replace all forms of reciprocating engines for electric power generation. But coal, on which was the dominant method of generating power back in the 60s, coal combustion, is the exhaust fumes or gases from that are not conductive. So a seed had to be added, and specifically a salt. And more specifically, potassium carbonate was added. You have to be above 2,000 degrees centigrade for that to form ions and be conductive. And that lends itself or has a consequence that enormous amount of heat is lost when it goes below that temperature of 2,000 degrees centigrade and becomes non-conductive. So you need massive recuperators, and you're at 100,000th the conductivity of what our plasma is. The power scales with the conductivity, thereby we're permitted to use very, very inexpensive permanent magnets versus superconducting magnets, and we can drive at a power density 100,000 times that of the conventional devices that were used in the past. Even at commercial scale, at 500 megawatt commercial scale, these things have been deployed, and that technology can be brought back with this new thermodynamic cycle and plasma producing reaction, and has tremendous potential for producing electricity for essentially all applications. And particularly, it would enable mode of transportation applications, cars, trucks, planes, train, marine, etc. This is a schematic of the magnetohydrodynamic converter. I showed you earlier a physical model. This is a picture of that. These are the parts. Basically, it's the electrodes and the magnets and the other components, the electromagnetic pump, recirculator, and like. What's very phenomenal is this conservative number, $25 a kilowatt electric, compared to more than $1,000 a kilowatt electric for rotating machinery. And this has no moving parts, and it's probably somewhere between 1%, more like 1%, the size and weight. So magnetohydrodynamic produces DC power, so it can be transformed or converted into AC power. And you could also use the DC power directly. Turns out essentially all loads, consumer electronics like computers and other devices, diode lighting, electric motors use DC power. So AC power is still used because let's say you're going to use a solar farm. You could use an inverter on a solar farm as well. In fact, that's what they're used for today. We'd use the same thing. So it's existing technology and it's getting cheaper and cheaper. But the inverter is required to make AC power. Then you have to use a transformer to increase it to very high voltage, like 50,000 volts. And you have to put it on transmission lines. Then you have to step it down in a transformer to a substation, then further at your home. And then ultimately it gets transformed into DC for your loads. Very wasteful, demand charges, transmission charges, all types of problems. At least it represents half the cost of electricity. Bypass all that, have power on demand at your home or business or mode of application. Another very unique situation is that we're going to have telemetry to monitor these sun cells. And when we have millions of sun cells, you have the potential of a 5G mesh network. So 5G mesh network is not possible because you still have to transmit the data over long distances using much lower data transmission rates because you have to use the longer wavelengths. When you have millions of nodes that are independent, you have the possibility you can have this 5G mesh network for all data transmission. And then you would eliminate the server farms and the vulnerability of the existing internet from electromagnetic pulse, solar flare, terrorist attack, other forms of natural disasters like hurricanes and the like. And it also will allow and is permissive of privacy because each one of the units is autonomous. Looking at the economics of SunCell, it's extraordinarily favorable. So, you look at the 300,000 watt cell, for example, you multiply that times, that's 300 kilowatts times the number of hours you run it per day, times the number of days, times the cost per kilowatt hour. So if you run it continuously at 10 cents a kilowatt hour, for example, that's about $260,000 a year in revenue. If you go to Japan or Caribbean or somewhere where it's 35 cents, you get up to $1 million a year potential revenue. So, and if you look at the worldwide market, as I was saying, just in replacement fossil fuel, that's about 10 trillion a year, which is represents a pretty good investment on the 120 million we've spent on this to develop it. And interesting because whenever you have a new disruptive technology, there's all kinds of new enabled scenarios. There'll be businesses that aren't even anticipated in terms of power to weight ratio for transportation and aviation and other commercial applications. It'd be creation of enormous amounts of wealth. You know, there's a lot of talk about a Green New Deal and 100 trillion for the US and how many decades it's going to take for everybody to agree to those terms and how devastating it would be on the economy. And this scenario, taking the world's peak generation capacity of 15 trillion watts If you manufactured 60 million SunCells and they were 250,000 watts per SunCell, that is 15 trillion watts continuously, not just peak power, and not hundreds of trillions, but hundreds of billions, and not decades. But if you take the fact that about 100 million cars are made a year, and the SunCell is much less complex with no exotic machining or tolerances or complexity and relative to a car, you could easily make 60 million per year, and you could go to zero CO2. At least feasibility, it would be possible to go to zero CO2 for the entire world in under a year with hundreds of billions and not hundreds of trillions. So that is a phenomenal development for something that seems to be one of the predominant concerns that the world faces currently. So we have a massive patent portfolio. This isn't even the full scope. They're constantly getting more cases issued. So this is wealth creation. So innovation and new technologies create new industry and new wealth for society. And this is sort of the ensuring that wealth creation event for the power industry as it deploys Hydrino power reaction and systems. So I want to thank you very much for your time and attention. I hope all stakeholders in the power industry get involved. This tremendous opportunity. You can find validation reports on our web page. You can see the address here. Oh, let me give it to you. www.brilliantlightpower.com. Technologies, validation reports for thermal systems and many different power applications we had done in the past. Also, under the publications, in particular journal publications, there's a paper that we submitted in supplemental for this world top tier journal validating hydrogen, 20 or more analytical signatures and spectroscopy data proving the existence of Hydrino with specific references to validation reports and selected papers of the more than 100 journal articles that we have published on Hydrino technology. To follow our new developments, you can go to our What's New webpage. We're continuously updating that so you can track our progress. And very much appreciate it. I'm going to take some questions. And then afterwards, we have a extraordinary heat transfer thermodynamicist, Dr. Mark Nansteel, who's going to talk about validation work that he did on the SunCell.
Thank you, Dr. Mills. So yes, a reminder, if you'd like to ask questions, please put them in the chat in the Zoom. And of course, yes, like Dr. Mills said, Dr. Nansteel, who did an independent review of his findings, will be here to talk in a second to run through it, of which you can also find on the website. So let me take the moderator's prerogative to kind of kick off the first one with Randy. Could you just real quickly kind of boil this down to what did we see today and where are we going from here?
Okay, we saw about say 25 to 30,000 watt input, and based on the data we have back in our lab, it's probably close to around 200,000 output. We ran it at lower temperature in the 450 range, which we have validation, independent validation to be about 30,000 in, about 130,000 out of continuously boiling steam that we run until the water level drops, that we have to add back water, which adds complexity to the energy balance. So then we stop it and take those numbers. And they're actually very accurate in terms of being conservative on the energy balance. The input energy is easy to measure because we have 10 microsecond sampling rate. It's a direct current and direct voltage. So it's just VI. It gives you the power input integrated over time, very simple. And then conservatively, we just weigh the amount of water that went off the steam, and we lose about 25 pounds in 2 minutes. And it's very easy to quantify that component of the energy loss. Of course, you can see there's other forms or pathways for loss. It gives us a very simple way of calculating. So you saw the SunCell producing at least 100,000 watts of extra power, and we're going to work with engineering firms to package that into commercial unit. So that would require sensors and controllers, programmable logic controllers typically used to control the ignition current, the glow discharge parameters that process the reactants, the hydrogen flow rate, the amount of the trace oxygen we add to form the trace HOH catalyst, the operating temperature and the pressure in the reactor, the flow rate of the electromagnetic pump, current, ignition current, etc., and the parameters thereof. So then when we made it to a heat exchanger, it will not be in a water tank. You can actually, when you're over there, you can feel the heat coming off. I can even see it here, the heat waves coming off that cell. So it warms up space and process and creates humidity. That's not typically how buildings are heated. They typically have a circulating water or blown like air vents and ducts to carry the heated air around. So that would require the mating of the heat exchanger, either air or water, to the SunCell, which is in progress in our facility, and also we're working to establish strategic partnerships with equipment manufacturers in that boiler and air heat exchanger sectors. So those are the main targets. We also have engineering designs and confirmed calculations on a 900,000 watt combined heat and power. So it'd make hot water and electrical power using a microturbine. And we're working to establish a program to make the magneto-hydrodynamic, so then we could address all applications, including heat, using resistive heat, and largely for the purpose of getting into the motive applications.
Thank you. Okay, so the first one here that we got on the chat is, have you looked at a reverse merger of a SPAC as a way to go public and raise capital? And also, who is advising you?
Well, that's getting a little into the confidential territory when you talk about who's our bankers and the like, because typically companies don't reveal that information. But I will say that we have looked at SPAC, Special Purpose Acquisition Company, and we're considering that amongst other avenues. And there's a mention of reverse merger and how that's not as desirable. SPAC seems to be a much more acceptable route in terms of what would be congruent with what industry would expect and investors in the larger community in terms of mechanism to be publicly traded. So we would be looking at SPAC, but right now we're looking at doing a private equity round to raise money to build the management team, because to be a publicly traded company, we need to build out the business and the ability to function as a publicly traded company. So that means a number of steps have to be executed. That is, we need to establish the engineering packaging deals, the original equipment manufacturer deals, green power pre-sales, and other strategic alliances and partnerships, and to get the compliance team, both on the accounting side and management side, to operate the company and to report and meet compliances for those that regulatory environment that's created by going public, and all above in terms of regulations worldwide and looking at different verticals like the thermal industry, industrial heating, residential heating, and then you've got air and you got steam and you got rotating machinery and every different category, stationary power for many applications. And then if you get into MHD, then you have all imaginable motive applications, many verticals, many territories, many deals to execute. So we need to establish those steps in order to go public. So we're doing the interim round with the mezzanine, and then on to some mechanism to go public. Either traditional IPO or SPAC are the preferred mechanisms.
Thank you. The next one comes here. How was gallium chosen as the heat exchange material? I know you also mentioned silver earlier, but besides gallium and silver, maybe also, I'm adding this to the question, mention some other potential metal materials that you've talked about before as well.
Well, the silver is unique because of that very special molten metal nanoparticle thermodynamic cycle that it enables. And silver is, it's for the amount of silver we use, it's really inconsequential to the capital cost, no matter what the price is relative to what it is today. And it will not move the silver markets appreciable because it's not a sustained consumption. It's only because once you build the sun cells and you exhaust the entire world capacity for power, it's only equivalent to less than 1 year's production of silver, and it can be recycled forever. So it from even the manufacturers of silver suppliers say it won't meaningfully long-term impact silver prices. So that seems to be a very viable, and there's multiple sources around the world in terms of supply chain. So that seems like a very viable material to use. There's also copper and nickel, which do not react with water. The only oxidant we have in our reaction mixture is trace amounts of water, which will react with gallium in high concentrations. But our continuous demonstration is proof that we are not oxidizing the gallium with that highly reduced reduction atomic hydrogen atmosphere with this reaction conditioning and the mixture that we're supplying to the sun cell. If it formed an oxide coat, the current would stop and the reaction would die instantly, even with atomic layer. So that's very important. And that had to be determined experimentally after we had been very far into the program, because you need to design and develop all the ancillary technology to run that in the first place to establish whether that's possible to continuously reduce gallium oxide under Hydrino power reaction conditions and get high kinetics and high power. So that was a very big breakthrough for us that works. Gallium has a very unique characteristic and property in that it's molten almost at room temperature. So you don't need heaters, you don't need to heat the top flange and all that. So we're using a feed through that's limited in its temperature. So if you use the silver cell, you'd have to run that at about 1,000 degrees centigrade, and that ceramic, there's a ceramic feed through that goes through the top to electrically isolate that top electrode. It can't survive at those temperatures. So this is really quite an ideal system, the way we have it set up, that you can run that flange colder and use molten gallium for thermal applications. It's just beautiful technology, and you circulate the gallium to an external heat exchanger. The silver, we use opposing dual molten metal injector electrodes, and we perfected that technology after a lot of work. We've solved the problem with the induction coupled heaters in terms of cold spots or changing emissivity or burning through the metal by having localized heating and melting in selective sections, and differential coefficients of thermal expansion, compatibility materials, and things like that. So that's been solved. But gallium is just very easy to work with because it's a liquid metal, essentially at room temperature. And if you add indium and tin, which in small amounts, it forms an alloy called gallistan. It's molten even to minus 19 degrees centigrade. So you can use it even in the Arctic, and it'd be molten just from the startup. So there's no real startup power involved with that. It can be instant on and instant power. So it's got a distinct advantage. And the other thing, it has the highest range of any element in terms of the difference between melting and boiling points, 2,300 degrees centigrade. So the vapor pressure can stay very low during a reaction. It's important because we're running this particular reactor at low pressure. And it's very safe. We have that cell, we've breached that cell where we burn holes in it. We show a lot on the videos on our webpage, burn holes in it right into the water tank. and liquid metal drips out, there's no catastrophic event because gallium has a huge surface tension. It forms a atomic layer oxide that protects it from further oxidation. We've had it blow out and form a kinetic energy jet right out in the lab. It's very, very safe because it forms this oxide coat and you can eat it. So it's got a lot of phenomenal properties that make it very conducive, particularly for this type of system, for the Brayton cycle and for the air and steam heating systems. Very, very favorable for those systems. But we could go the copper or nickel that will not form an oxide with water and use those, or the silver, and particularly that has the advantage of enabling the magneto-hydrodynamic technology.
Thank you. Here's one coming from somebody. He says, we own 60 affordable assisted living communities, 90,000 to 120,000 square feet in 3 to 5 stories. How could Brilliant Light Systems replace electric and gas sources? He did mention as an aside, some of the communities use solar as well, but really how would BrLP systems replace some of the electric and gas sources they use today?
Well, as you saw in the demonstration, we're producing heat, and heat was going out in the room. So whatever power we make has to heat up the air. It's heating up steam. That steam's going out into the space and heating it up. So to make it into a practical commercial device, we would make the SunCell external to the water tank, to the heat exchanger, and flow water through the heat exchanger or air through the heat exchanger, and put that through your ductwork. So if you're using natural gas or some other means of heating water and circulating that, or heating air, we would just replace the source of heat, be it electrical. I don't know if you're maybe using solar thermal. We'd take all the plumbing and sunlight absorbing sections out and just put in our SunCell with phenomenal reduction in complexity, cost, maintenance, and displacement.
Thank you. A couple more here, and then we'll get to Dr. Nansteel. One here, have you considered grants from the DoD, given the weapons potential?
Well, we do have a specific subsidiary, a fully owned subsidiary called Blacklight Innovation. And we set that up specifically to segment that off from our power business. And we were considering pursuing energetic materials, other military applications, but we felt it best to focus on the civilian power business because there's just tremendous need for that and a tremendous demand for a clean power source. But we do have a vehicle where we could do black programs and other things that would separate it from our core business, that we could keep the two.
I'm going to jump back to just a couple of questions we got from some of the prior demos earlier, the other 5 that I thought were really helpful and good to maybe get your insight here too. One came, why are so few people aware of this at this point in time?
Well, it's not because we haven't put out validations or papers. We have over 100. I think we did 50 meeting presentations. Lately, we've just been focused on like the last 3 or 4 years on making a product, because typically we get to the point where we would have, say, a Caltech professor or somebody with a PhD from Caltech or MIT or some luminary, or we had a Fortune 500 defense contract, all types of validations. You can see those on our webpage. And we'd always get to the point where they'd say, well, it works, but it's not commercially viable. And then some quantum physicists would say it's impossible. And then the perceived risk was too high, that it wasn't going to work, that it would be thrown back to us to put into a commercial product. So there's 2 categories. there's either defeat quantum theory, which we can do now on demand. We can show there's a new state of hydrogen. So you can't say it's theoretically impossible because in reality we have it. So we've basically surmounted that challenge. And simultaneously, we now have a commercial product. And you would think they go hand in hand because now we can make enough hydrino because we're making massive power that the two came to fruition simultaneously. So we can answer those questions. So we think everyone in the world is going to know about this very soon because we're going to keep demonstrating it and demonstrating it. And we do have another criteria that's in process, and that is, I won't believe it until it's in the top journal in the world by someone who's completely independent, who has no relationship with you at all, who's a noted world expert and publishes it in this top world journal. And that is in progress. That data exists, and eventually it will come out in a very, very top journal. And there's many more in the pipeline that are working on these types of validations, and it absolutely proves hydrino. And that's what they're saying. This is no question a new state of hydrogen. So it will be known, we think, shortly, but you can understand something this disruptive met with a lot of skepticism and a lot of activism to suppress it because it challenges so much dogma, and people listen to these experts, and that it was perceived at risk. So we were left on our own devices to bring it to a commercial scale. Okay, so I want to introduce now Dr. Mark Nansteel, who is a phenomenal individual. He's has a PhD from Cal Berkeley, and he's a noted thermodynamic expert. In fact, we had an engineering firm in Boston that we engaged to do some very complicated thermodynamic analysis, and they reached out through their network to what they perceived as the top expert in thermodynamics in Boston. And even he said in an email to me, Mark is he's in a category of his own. So I'm going to turn it over to Mark. We're very proud to have him involved. We think he does tremendous work, and he's got some good things to tell you about the SunCell.
Thanks, Randy. Yeah, over the past year or so, I've done validations for a number of calorimetric tests of the SunCell for BrLP. We didn't do calorimetry today in the demonstration because of time constraints, but it's a very straightforward process, the calorimetry for these devices. There's just two kinds of measurements that are necessary. There's a measurement of the electrical energy input to the cell, and at the same time, we measure the thermal energy release from the cell to the water bath. For the electrical energy input, there's really three things going on there. There's the low voltage, high current plasma maintenance energy. There's also a smaller energy that's related to driving the gallium streams, recirculating that, and a similarly sized quantum of energy that's related to maintaining the glow discharge, which dissociates and ionizes the gas to form the catalyst. If you take those three pieces and put them together, those three electrical energy inputs, you come out to about 8,000 kilojoules of energy for a 5-minute calorimetric test. So that's the input. On the other hand, the thermal energy release, there's only a couple things going on there. There's a sensible heating of the water. That's the kind of heating that makes the water temperature rise. And there's also vaporization energy. And that's reflected in the boil off that you saw earlier in the demo. If you add those two energy release mechanisms together, you get 25,000 kilojoules. So in summary, you add in 8,000 kilojoules of electrical energy, and you absorb in the bath 25,000 kilojoules of thermal energy. So the difference there, 17,000 kilojoules, that's the energy that's coming from the plasma reaction. It's a very sort of obvious and very conclusive result, because that 17,000 kilojoules of excess power is more than twice the magnitude of the input energy. So it's it's a sort of an obvious result in the calorimetry. And if you're interested in the details of that calorimetric analysis, you can find that on the website. That's where the reports are, the validation reports.
Thank you, Dr. Nansteel. If I might, may I ask you just one more question here? Obviously, you walked through the energy input and of course, the energy output and analyzing that where it was very easy to explain. Could you just add one more insight as far as how much hydrogen, oxygen are we putting in? Because that obviously is also another input, of course, into all this.
Yeah, well, there's a very, very small amount of oxygen that's flowing through the system. It's actually on the order of only 1 or 2 SCCM. So that's really limiting the heat of reaction in that oxygen and hydrogen reaction. Turns out if you do that simple calculation, the enthalpy of that reaction for the entire 5-minute calorimetric test, it's about 100 joules of energy released from that reaction. So you're comparing 100 joules of energy to 25,000 kilojoules. That's that's 6 orders of magnitude difference. So that really, it doesn't substantially enter into the calorimetric result. Thank you.
Yes, thank you, Dr. Nansteel. Thank you very much for your insights there. I also want to thank everybody for joining this afternoon for the final of our 6th demo here the last 2 days. I also want to give a big thank you to Dr. Mills and his team for a really nice job. Literally everything went flawlessly and worked perfectly for their first field test on the road. So we look forward to seeing you on the road on another field test. And also, if you have any questions, feel free to reach out to us and we will work on getting your questions answered. Thank you very much and have a nice weekend. Bye-bye.